Hi everybody. Today is really a great day in a geometry class. Today I get to introduce one of the most powerful things that you'll get to learn from me in this high school geometry class. It's about the trigonometric functions. Lots of the things we use are just good tools to learn and to get better at mathematics. But trigonometry in and of itself is really a special thing that you're going to want to remember for the rest of your life. And clever people will use it throughout their lives. But let's jump right in. We will study the three basic trig functions using special right triangles. That's just first, and then we're going to apply it to real-world circumstances right away. Assign the most simple proper lengths to the two triangles. And here we've got a 30, 60, 90 triangle. I hope you already know what would be the simplest possible numbers that would fit on the sides of a 30, 60, 90 triangle. I'd make the short side be 1. For some interesting reasons I've shown you, the hypotenuse would have to be 2. Use the Pythagorean theorem, it turns out the longer leg is the square root of 3. And those are ratios that you just got to remember. Now this guy, it's a 45, 45, 90. If I made this leg be 1, I think this one would have been 1, because when two sides are congruent, when two angles are congruent, the sides opposite them would have to be congruent. The converse isosceles triangle theorem. And if I were to use the Pythagorean theorem, the hypotenuse would be the square root of 2. So I got to remember that too. And I'm thinking that you do. The sine of an angle in a right triangle. The things that we're going to learn at first only apply in right triangles. However, we will generalize and be able to do it in all kinds of triangles, acute and obtuse. But to begin with, in a right triangle, by definition, the sine of an angle is given by the ratio of the opposite, notes that you ought to take, over the hypotenuse. The sine of every angle in a right triangle will always be given by the opposite over the hypotenuse. That's a ratio. The cosine of an angle, also in a right triangle, is given by the adjacent leg over the hypotenuse. That would be the ratio known as the cosine. And the tangent of an angle in a right triangle is given by the ratio of the opposite leg over the adjacent leg. Knowing those three can give us the power to do lots of clever things. The stuff I'm going to show you right now, and what we're going to do for the next couple of weeks, as long as we're doing trigonometry, would behoove you to have a calculator. You're going to want to get a calculator. It ought to have a sine, a cosine, and a tangent button, and an inverse button. Lots of calculators have that for not too much money, probably $10 you could have one. If you had a graphing calculator, that's fine, but that's what I'm going to use, but I don't really need it. I'm going to find the exact value. Now, notice here it says the exact value. I'm not going to have a decimal approximation. It's going to be the exact value for the sine of 30 degrees. And that'll be easy. Watch this. The sine of any angle is given by the opposite over the hypotenuse. I'm going to find a 30-degree angle. Here's one. And the opposite over the hypotenuse would be, this is the opposite leg, and the hypotenuse is 2. So the sine of 30 degrees has got to be a half. We'll look at a calculator and verify that in a minute, but yeah, that's what it is. Let's do the cosine of 45. Now, how does one get the cosine of any angle in a right triangle? It must be given by the adjacent over the hypotenuse. That'll be a ratio. So we're going to find a 45-degree angle. You can use either one of these. It'd work the same. I choose to use this one, and I'm going to show the adjacent leg over the hypotenuse. Adjacent to this angle is 1. The hypotenuse is the square root of 2. So on first thought, I would say 1 over the square root of 2. And that is the good value. But we've grown accustomed to, and it's important that you realize in this class, we're not going to leave a square root in the denominator. So I'm going to multiply by the number 1. There's the good value, but I'm not going to alter that value. I'm going to change its appearance. I'm going to multiply by the square root of 2 over the square root of 2. That's essentially the number 1. When I do that, I get the square root of 2. And the square root of 2 times the square root of 2 is just a plain old 2. And when anybody ever asks you for the cosine of 45 degrees, don't tell them 0.707. Tell them the square root of 2 over 2, because that's the exact value. Let me hit that with a calculator and show you that that's true. I think I got this set up so you can see it. First, I'll do the sine of 30. I'm going to turn on my calculator. I'm going to check the mode. And right now, you might see that it is in degree mode, and that's good. We're going to have to use degree mode. And then I'm going to type in the sine, and there's the sine function, and I'm just going to tell it of 30 degrees. And the sine of 30 degrees tells me 0.5, and that's pretty good because we said it'd be a half. Now what about the cosine of 45? Let me try that too. The cosine 45 tells me how to be 0.707. See if we get a good look at that. But then we thought it was the square root of 2 over 2. Let's see if that's pretty close. So I'm going to type in the square root of 2, close those parentheses, divided by 2. And check that out, would you? They're exactly the same. To 10 decimal places, the square root of 2 over 2 is the cosine of 45 degrees. It's not 0.707. That would be useful if you were trying to find the length of a flagpole or something like that. Yeah. Use 0.707. But if I ever ask you, what's the cosine of 45 degrees, you can tell me the square root of 2 over 2. And now, let's do some more. See how much fun this could be. The tangent of 60. How in blazes could I possibly find the tangent of 60? Well, how do you get the tangent of any angle? The tangent of an angle is given by the opposite over the adjacent leg. There's a ratio of the opposite and the adjacent legs. So go find a 60-degree angle. These are pretty powerful. There's a 60-degree angle. And so how would I get the opposite over the adjacent legs? What is opposite of the 60? And that's the square root of 3. And what is adjacent to the 60? Now you might think these are both adjacent to that 60. But the 2 is the hypotenuse, and we'll always call it the hypotenuse, so 1 is the adjacent leg. So when I look for the tangent of 60 degrees, I should look for the opposite over the adjacent. Opposite the 60 is the square root of 3, the adjacent is 1. So I declare that the tangent of 60 is the square root of 3 over 1. Now that's not something you want to memorize. That's something you want to be able to decipher anytime you have to. I'm going to give that a look and see if that's true. Let's check out the tangent of 60. I think it's good for you to see this. Tangent 60 degrees. It tells me about 1.732. Now, I think I'm going to take that and I'm going to square it. Let me go second answer. Let me not do that. Let me just take the square root of 3, which is what I ought to do. And I get that number. Had I squared it, I would have got 3, but that's not what's important. But you would agree with me that the tangent of 60 is the square root of 3. And the calculator does agree to 10 decimal places. You work out the sine of 60 and the cosine of 30. You have an interesting relationship, those two will. In class, I'd shut that video down, you'd figure those out. At home, you should do that too. The sine of 60. How do you get the sine anyway? Opposite over hypotenuse. So go find a 60-degree angle that you know a lot about. And give me the opposite leg over the hypotenuse. That's got to be the square root of 3 over 2, huh? And you'll look clever in your calculus class when the guy says, hey, what's the sine of 60 degrees? You tell him the square root of 3 over 2. So remember how that happens. Remember these triangles forever. Remember these relationships with sine, cosine, and tangent. I'll show you a way to memorize that pretty quick. Cosine of 30. Okay, how's one going to get the cosine anyway? Cosine is given by adjacent over hypotenuse. Go find a 30-degree angle, that's this one. And the adjacent leg for that 30 is the square root of 3. And the hypotenuse is the 2, so it's going to be the square root of 3 over 2. Well, that's kind of interesting, isn't it? The sine and the cosine of these complementary angles are equal. Yeah, cofunctions of complementary angles are equal. That's something you'll learn in your trig class, or you should learn in your trig class, but that's not a topic for today. Let me just type in the sine of 60 and get a look at it. That you verify that this is true, and that's what the sine of 60 is, according to the calculator with a lot of decimals. But I'll type in the cosine of 30 as well. Let's compare those two, and they do look pretty close, don't they? Yeah, those are the same darn number, and I bet it's going to be the square root of 3 over 2. Let's check on that. Square root of 3 divided by 2. Yeah. So, I think you're going to agree with me that this is a very lovely way to know the sine, cosine, and tangent of a bunch of angles, 30, 45, and 60. Actually, they show up in many more places than that, but for right now, that's great. Let me just show you a little something. You did a question just recently where you had to find the height of a palm tree. And the guy cited to it from a distance. I don't really remember what the distance was. I'll say it was 40 feet. I really don't remember. And this angle was 30 degrees. And this was a 90. and you're able to find the height of that palm tree. And that was because you said, well, this is a 30, 60, 90 triangle. And this would be the longer leg opposite the 60. And if that length was 40 and you divided it by the square root of 3, because that's how you go from the longer leg to the shorter leg, you have to divide by the square root of 3. That would have become 40 square roots of 3 over 3. We'll talk about how that happens, but that would have been the height of that palm tree. I'm going to find that out real quick. It's not important, but I think it's probably a good thing to see. 40 square roots of 3 divided by 3. Ooh. Oh, I did 400. Let me do that better. I think it would have been about 23 feet up there. Let me go with 40, square roots of 3 divided by 3. So for this situation, that would have been 23 feet tall. But my point is, what if it weren't 30 degrees? What if that angle had been 25 degrees? What would you do then? You say, I can't do this? What if that angle had been 48 degrees? What would you do then? Well, you couldn't use these special right triangles, but you could use trigonometry. That's really the beautiful thing here. We can use these things for any kind of right triangle. While you have memorized the ratios for 30, 60, 90s, and 45, 45, 90s, the calculator has memorized all the ratios for all of those angles. 22 degrees, 48 degrees. So let's get down here and let me just show how it works. Angle A is 22 degrees here. And AB, this guy's looking at the top of a flagpole, and it is some 60 feet away. And we're going to find some other lengths. This flagpole is perpendicular. We've got a right angle here, so I can use this right triangle trigonometry. Find the length of AC. Maybe I'm going to find this length first, huh? And the first thing you have to think through here when we're finding these lengths is, what function would I use? Would I use the sine, the cosine, or the tangent? And this depends on what do you know and what do you want to know. And if I concern myself with this 22 degree angle, what do I know? I know this 60. I know the adjacent leg, don't I? Adjacent to that 22 degree angle. What do you want to know? I want to know the hypotenuse, don't I? So, because I know the adjacent and I wish I knew the hypotenuse, I'm going to concern myself with the function that uses adjacent and hypotenuse. That's got to be the cosine. That's how we're going to make those kinds of decisions. From the diagram. Okay, so what function should be used? And I'm going to declare that to be the cosine. And then we're going to show how that could be used. First, I'm going to give the cosine of this 22 degree angle from my diagram, from this picture. So over here, we're going to do how people abbreviate cosine. They just use COS for cosine like it is on the calculator. And we're going to type in the cosine of, well, we're going to write down the cosine of 22 degrees. Well, according to my diagram, what is the cosine of 22 degrees? And recalling the cosine is adjacent over hypotenuse. Adjacent here would be 60. And the hypotenuse, well, that's what we're trying to find out about. And for right here, for clarity, let me call it AC. So I got it once from my diagram. Now I'm going to get it from my calculator. I'm going to say, hey, calculator, what's the cosine of 22 degrees? And it knows that. Merciful heavens, cosine of 22. And we're going to agree to go 4 decimal places here. I'm going to call that 0.9271. Now I have to call that, let me get a good look. Yeah, 0.9271. From my calculator, the cosine of 22 is 0.9271. It says give the length of AC. Something about these two statements should allow me to find the length of AC. I hope you're thinking what I'm thinking. This is the cosine of 22 degrees, and this is the cosine of 22 degrees. So those two things got to equal each other. We're going to write a ratio. This is truly a ratio right here. This is 0.9271 over 1. These two things are equal. Let's compare them. 60 over AC is equal to 0.9271 over 1. And I got to cross multiply and divide here. I'm going to get 1 times 60 is just 60. is equal to 0.9271 AC, which is what I care about. Let's divide both sides by 0.9271. And that ought to give me the length for AC, huh? Just that quotient right there. I'll hit that with my calculator. You should too. I think I got that right. 60 divided by 0.9271. So that tells me it should be, let's round lengths for problems that like this that we're solving to the nearest tenth. So I would call that 64.7. Give the length of AC. AC is 64, excuse me, 64.7. Okay, that's one. We've got something figured out already. 64.7 is just about what that ought to be. But then let's go find BC. Let's find the height of that flagpole. I'm sure that's what you were wondering about all along, wasn't it? Okay, let's figure that out. We can call it F, and we're going to write proportions and figure it right out. I would lay off of that 64.7 because it's a calculation that we're not exact with, but with this 60 we are exact with, so I'm going to use this in my next calculation. You could use the 64.7 and be pretty darn close, but I'm going to find BC, and I'm going to concern myself with this 22-degree angle. And first I got to figure, which function am I going to use? Well, that's the first thing I'd ask you. And you got to think, well, what do I know and what do I want to know? I wish I knew the opposite length from the 22-degree angle, and I do know the adjacent length. So I should use the function in this group that uses opposite and adjacent. So that's going to make me use tangent, huh? Well, here we go then. What function would we use? The tangent. Now, one time from the diagram, and to abbreviate tangent, what we all will do is use TAN. And people do say tan. People also say cos, but I wouldn't. I would just say cosine. The tangent of, and then we're going to stay with that 22-degree angle. The tangent of 22, since tangent is given by opposite over adjacent, the tangent would be opposite of the 22, that's the flagpole, over the adjacent, which is 60. Okay, where was I? From the diagram, the tangent of 22 is equal to F over 60. Tangent is opposite over adjacent, so the tangent of this angle would be the opposite over the adjacent. There it is right there. Now I'm going to get that from my calculator. The calculator knows the tangent of 22. You don't have to memorize anything like that. Tangent 22, we'll take it to 4 decimal places. That'll be the common way we'll make this happen. 0.4040. Write it out like that, man. The tangent of 22 is 0.4040. And we're going to think about these two things and the way they work together. Since this is equal to the tangent of 22, and that is equal to the tangent of 22, the tangent of 22 is not going to change, so these two things that equal the same thing must equal each other. You must be thinking that F over 60 is equal to 0.4040 over 1. I'm going to cross multiply, we'll have it, huh? 1 times F, just F, equals 0.4040 times the tangent of 60. No, excuse me, 0.4040 times 60 itself, huh? Excuse me. Oh, I've got that wrong, excuse me. You're ahead of me. How about 24.24? Took me a minute to get it right. That's how tall our flagpole is. Just something we ought to check. Why don't you hit it with the Pythagorean theorem in your calculator, see if it adds up pretty well. It should, shouldn't it? I think I could maybe make that happen. Let's go with 60 squared plus 24.24 squared. Gives me that. Oh, I typed that in wrong. Doggone it. Let me do that again. I apologize. 60 squared plus 24.24 squared gives me that. What if I took the square root of that? I hope it'd be pretty close to this, huh? Because there I've squared the lengths of the legs. Let me take the square root of, oh goodness gracious. Let me go back. Well, let me not worry about that. Hit it with the Pythagorean theorem. I can do that better. I just made a mistake and I apologize. There, I finally got it right. I went down a matrix path. I don't know how. But 60 squared plus 24 squared ought to give me the hypotenuse squared. I took that, took the square root of it, and it tells me about 64.7, so I'm pretty happy with that. Pythagorean theorem does apply. We don't got to check the Pythagorean theorem every time, but it's just a nice thing to see that it would apply. Let's do some more. This is a very interesting section right here. We should take the time to think carefully about it. Yeah, we used this thing to find lengths, didn't we? Just a moment ago, we were able to find the height of the flagpole and the length across the ground from the man to the flagpole base. You can find lengths in triangles when you know trigonometry. But you can also find angle measures. And watch how we do that. Generally, with a trig function, the input or domain is, when you take a trig function, like you'd be thinking of the tangent of 60, or maybe the cosine of 45, or maybe the sine of 20. So the input, the thing that you find the tangent of, cosine of, or sine of, is an angle. And the output or range of that trig function, like when you took the tangent of 60, I think that was the square root of 3 over 1, and the cosine of 45 was the square root of 2 over 2, and I don't know the tangent sine of 20, nobody does, but it's some decimal thing that is a ratio. The output or the range of a trig function is a ratio. When you do trigonometry, you input an angle and you output a ratio. But if you do inverse trigonometric functions, which is the way we're going to use the system we're going to use to find angle measures, it switches the domain and the range. Thus, the input of an inverse trigonometric function will be a ratio. And the output or range of that inverse trig function will be an angle. And that's what we're going to try to get anyway. We're trying to get the measures of those angles. Let's take a look at this one, for example. We're going to find the measure of angle A. And this is a right triangle, and I do know this length and I know this length. I ask you, do you know could you apply one of those trigonometric functions here? And then, so I guess I'll have to cut to the chase. And let me give you a quick way of remembering these trig functions. There's this old Indian word, not really, but we call it the Indian word SOHCAHTOA. If I write SOHCAHTOA, lots of people will know this word. SOHCAHTOA is a mnemonic device, so you can remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So man, remember that. It's very, very helpful. So I'm going to find the measure of angle A. What do I know about angle A? Do I know its sine or its cosine or its tangent? What do I know about angle A? I know its opposite length, the opposite leg, and I know the hypotenuse. Let me make a statement. The sine of whatever angle A is given by the opposite over the hypotenuse, so that must be 8 over 17. It's got to be true. The sine of this angle is the opposite over the hypotenuse. So if I would like to know the measure of angle A, the interesting thing I got to do is I have to take the arc sine of both sides of this equation. The arc sine is the inverse sine. When you take the arc sine of the left-hand side, it just destroys the sine, and you're just going to be left with the measure of angle A. On the right, let's write this time the arc sine, and here's how you would write that. It looks like an exponent of -1. It's not really an exponent. It just denotes that we have an inverse function of 8/17. That's what we got to type on our calculator. And I'll get that right. You can too. It's no big deal. So I just cleared my calculator, and I have to go second sine. And if you get a look at that, that's showing the arc sine right there, isn't it? A little glare, but now I just got to type in 8 over 17. 8 divided by 17 And the arc sine, I like to say instead of arc sine, the angle whose sine is 8/17 is 28.1 degrees. We're going to round angles to the nearest tenth, and that guy would be 28.1 degrees. Measure angle A. That's pretty good. We got a measure of an angle. 28.1 degrees. Find the measure of angle B. Now, you might be saying, hey, I know 90 went there, so these got 90 to share. I'll subtract this from 90. I'll know angle B. I said, no. Let's get some trigonometry going. What else do you know about angle B? Do you know one of the trig functions? So I think about angle B, and I think, well, what do I know about angle B? I don't think it's congruent to angle A. I don't know that's true. Actually, I do know this is 15 by Pythagorean triple, and we could talk about that if we needed to, but we could ignore that for right now. I know it's not isosceles, but if I know about the 8 and I know about the 17, what do I know about this angle? I know about its adjacent leg and its hypotenuse. And adjacent and hypotenuse, that's cosine, huh? So as I go looking at angle B, I'm going to write that the cosine of angle B. I have to choose what function to use, and that's how you decide, what do I know and what do I want to know? I want to know the cosine of this angle. Asks me to. Well, actually, it tells me to find the measure of angle B, and I have to go with what I do know. I know the cosine of angle B is 8/17. So what can I do to get the measure of angle B? Last time we took the arc sine of both sides of this equation. You're going to take the arc cosine of both sides of this equation. The arc cosine destroys the cosine. You're just left with a measure of angle B. Right at this time, the arc cosine of 8/17. Let me get that from my calculator. It ought to be the complement of this angle. They should add up to 90 together. Yeah. Let me clear the stuff that I have and say arc, that's second, cosine. So you see I have the arc cosine function showing. Then I'm just going to type in that ratio. 8 divided by, 8 divided by 17. Thank you for being so patient with me. I make little mistakes. Let me delete that. There we go. Sorry about that. 8 divided, or cosine 8/17. I got 61.9. Degrees, huh? That was the measure of that angle. Now check those out. They look like they're going to add up to 90 to me, huh? So it does seem like this is working pretty well. Let's do that again. This is a little mixed practice. What could you do to solve these? I think I'll